What we hear is the sound of the prime numbers, and what we see is the wall of prime factors, and its reflection in the water. A prime number is a whole number that cannot be divided into two or more equal parts greater than 1, and a whole number that can be divided this way is a composite number. By the fundamental theorem of arithmetic, every whole number greater than 1 is either a prime number itself or can be represented as a product of prime numbers. And this representation is unique, disregarding the order of the factors. 1 is not a prime number, because if it were, this would have been 3 different prime factor representations of the same number, and we can't have that. There are 35 primes among the 151st whole numbers. In a 6 by 25 grid, their distribution seems a bit random. But in a 5 by 30 grid, a pattern emerges. The pattern becomes even clearer when we map the composite numbers to their least prime factors. As we see, factors 2, 3, and 5 are all aligned in their respective columns, but 7 is not. To get a pattern where 7 fits in, we need 7 times 30, which is 210 columns. And to fit in 7 and 11, we need 7 times 11 times 30, which is 2,310 columns, and so on. The numbers 2, 6, 30, 210, 2,310, etc. are the primorials, the factorials of the primes, as it were. For the product of the n first primes, we write p subscript n number sign. And for the product of all primes less than or equal to n, we write n number sign. So for instance, p5 primorial equals 11 primorial equals 12 primorial equals 2 times 3 times 5 times 7 times 11 equals 2,310. When Pn is the nth prime, O is the primorial of Pn, and k is a whole number greater than or equal to 0, then ko is a primorial point. The interval from one primorial point to the next is the primorial period, and the same interval shortened by 2 numbers at each end and mapped to unique factors less than or equal to Pn is the primorial symmetry. The third prime is 5, and the primorial for 5 is 30. And here is the symmetry for 30. Primes greater than 5, 7, 11, 13, 17, 19, and 23 are not part of the symmetry. And the powers of 2, 3, and 5 in 4, 8, 9, 12, 16, 18, 20, 24, 25, 27, and 28 are represented by 2, 3, and 5 alone. Placing different factors on different levels makes the symmetry stand out more clearly. The first non-empty symmetry is that of the 3 primorial, and the second is that of the 5 primorial. A primorial symmetry remains unchanged through all primorial periods, as exemplified by the 3 primorial symmetry throughout the first 5 3 primorial periods. Here is the 5 primorial symmetry again, and here is the 7 primorial symmetry. In a slightly different arrangement, we use prime factor blocks, which are akin to Cuisenaire rods and having lengths equivalent to prime values. So we have 2 blocks, 3 blocks, 5 blocks, and so on, and place the 2 blocks in the bottom layer, the 3 blocks in the layer above, the 5 blocks in the layer above that again, and so on. Given 2 adjacent layers of p blocks and q blocks, since p and q have no common factors, it takes pq blocks and qp blocks to make the block ends align. This gives a 2-layer wall section of length p times q. Adding a layer of r blocks, since p, q, and r have no common factors, it takes p times q r blocks and r p q sections to make the block ends align. This gives a 3-layer wall section of length p times q times r, and so on. Here is a handful of alignment sections, just to assert their symmetric nature. In each layer of an alignment section, all blocks have the same length, so the layer is symmetric about its middle, and when all layers in the section have the same length, and all are symmetric, the entire section must also be symmetric. And now the prime factor wall. One might be tempted to describe it as the primeval wall, reflected by the primordial sea, but an idealist would point out that the prime factors are prior even to the first age, and their reflection prior to the first beginning. Well, whatever. In any case, the music, the colors, and the sea is all just decoration. We zoom in on the first couple of primordial 7 periods, each 210 units long. The blue poles mark the primordial 7 points, and the red poles further out mark the primordial 11 points. The primordial 11 period has length 2310. The full length of the wall section we are watching now, the 13 primordial section, is 30,030, 13 times the 11 primordial. The length of the next primordial is 17 times that again, 510,510. And the next one is 19 times that again, 9,699,690. And clearly the corresponding wall sections extend way beyond any meaningful visual perspective. So rather than trying to behold the vastness of the wall all at once, we go directly to the primordial points. A primordial point is where one primordial period ends and the next begins. The vertical line in the middle is where all the factors in each of the 2 period sections align. Given a prime p, its primordial O, and a whole number d less than or equal to half O, then ko plus O over d, and k plus 1 O minus O over d, for k greater than or equal to 0, are symmetric subpoints in the primordial period from ko to k plus 1 O. First we just race through the denominators 2 through 360, and then we take a little more time with some of the categories of subpoints. If q is a prime less than p, then at O over q, we will see the same as at O, except that q will not be aligned with the other factors. The denominator can contain any number of unique prime factors less than p, and the more we put in, the more the alignment line will be disrupted. If the denominator d is a power of subprime q, or a composite of prime powers, the subpoint O over d looks like the subpoint O over q, but since d is not a prime, we do not get an alignment line. We do get a defined center though, shooting out rays of prime factors. The number of rays grows as the denominator grows, but their density, and hence their visual definition, decreases accordingly. So far, we have kept the bottom of the wall in sight. The higher up we get, the more open and dull the wall seems. But when we ascend above the dense layers at the bottom, we can compress the rest of the wall horizontally, making its higher realms look maybe a little more interesting. Here we start at prime number 50, which is 229, and the width to height ratio is about 1 to 10. And now a brief note on the music. The sounds we recognize as having pitch, expressions of musical notes, have the wonderful property that when the frequency of the vibration that produces the sound is doubled, it sounds the same, only 1 octave higher. And when the frequency is halved, it still sounds the same, but this time 1 octave lower. This means that sound has an intrinsic modular quality. If we, for instance, divide the octave into 12 parts, the way it's done in Western music, we can actually play a sequence of whole numbers by mapping each number modulo 12 to a corresponding note in the octave. And we can expand the range to 2, 3, or 4 octaves by taking the numbers modulo 24, 36, or 48. And this is how the music in this video has been made, by using the prime numbers as input. We'll let the music play along as we drift across subpoint 216 on the right side of the second period of primordial 7329. This last part is meant mostly for entertainment. And if one is not entertained, one can stop the video without loss of information.